Stripping down science. The Naked Scientists.
Hello, it's Sunday, February the 13th, 2011. Welcome to The Naked Scientists with me, Chris Smith.
With me, Diana O'Carroll.
And with me, Dave Ansell.
This week we're taking on your science questions. We'll find out what makes mucus, otherwise known as snot, green, what would happen if two lightning bolts collided, and is a hole left underground after the oil and gas have been extracted? Diana.
And also this week, news that scientists studying our early human ancestors have made a big step forward in understanding when they first began to walk on 2 feet, and evidence that eating oily fish can reduce the risk of developing some common forms of blindness.
And in kitchen science, I'll be finding out why this happens. If you hit a balloon across a room really fast, initially it travels straight, but then something quite strange happens. Try it for yourself and find out later in the programme what you're seeing and why you're seeing it.
So if you want to ask us a question, please get in touch.
To contact us through Twitter, tweet at Naked Scientists, or you can write on our Facebook page. That's at nakedscientists.com/Facebook, or you can, of course, email us. It's chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
This is The Naked Scientists with Chris Smith, Diana O'Carroll and Dave Ansell. And let's begin by taking a look at some of this week's top science news stories. Diana, what have you got for us?
Yeah, big news this week about the ability of Australopithecus afarensis to walk like a human. Researchers have found that this species of early hominin had rigid arched feet, and this means that afarensis would have spent a great deal of time walking only on 2 feet, which is just a step away from full bipedalism. Now, researcher Carol Ward and colleagues from the University of Missouri have come to this conclusion over a fourth metatarsal. Now, that's the Wayne Rooney foot bone, for those that don't know. Found in Hadar, a well-dug fossil site in Ethiopia, this metatarsal is a perfect example of a bone which was lacking in the famous afarensis specimen known as Lucy. So publishing in the journal Science, the researchers think that this bone points towards arched feet because its two ends are twisted in relation to each other. And now that means that one articular surface, where it meets the cuboid, that's one of the more sort of lumpy bones that makes up the body of the foot, sits at a different angle to the surface where it meets the phalanx, which is essentially in the first row of toe bones. Now this means that the foot was very unlikely to have just been flat, and it would have been quite well adapted to the push-off motion that's required in walking or even running. And it fits in well with what we already know of afarensis' hips and spine, which do suggest quite upright walking, something which a chimpanzee can't do as efficiently.
Because I was going to say feet and hands are really rare in these kinds of fossils, aren't they? Because for some reason, probably because the bones are really small, they're very rarely found. Exactly
that, they're just so small. And it's usually sort of the thicker parts of the skull, and occasionally you get some ribs, but spine that sort of turn up. But walking on 2 feet is something quite rare to find about 3.7 and 2.9 million years ago when afarensis lived. But it could have made regular tool use possible. We don't know for certain that Lucy would have used stone tools, but there was a study that came out last year in Nature by Shannon McFerrin and colleagues, which did seem to suggest that tool use was going on 3.4 million years ago. Now, this would make perfect sense if you have an early hominin who's walking around with 2 feet and has 2 hands spare.
Had people previously suggested that Lucy and those like her would have walked upright, or had they thought that perhaps she did a bit of both?
Yeah, I think they didn't think she would have walked upright quite to the level that this foot bone suggests. I mean, that, as I said, her spine has the kind of double curve in it that the human spine has, which suggests she could be quite upright, and also the hips are sort of indicative of bipedalism.
But this is the real nail in the coffin. It really does drive the message home. Exactly. Looks like that was the case. Thanks, Diana. Dave?
There's been a new way of seeing inside any body or inside flesh, and it's been developed. It's just using normal visible light. Now, light's a great way of imaging and things. We do it all the time, and it's great for probing biological material. And it's also used in therapies such as photodynamic therapy, where cancer patients are injected with a chemical that only becomes poisonous when it's exposed to light. That way you can minimise the effects of chemotherapy and only poison the bits of the body which have actually gone wrong in the cancer. The problem is that despite the fact that flesh doesn't absorb that much light, it does scatter it very, very strongly. Which you'll have noticed, you ever shined a torch on your hand, instead of seeing the light go straight through so you can see the torch, just your whole hand starts glowing red. This means that focusing light onto something more than a couple of millimetres below your skin is virtually impossible. However, all light paths are reversible. So if you put a light bulb in the tumour and worked out how the light was leaving the body from that tumour and then reversed its path, it would all then get sort of refracted and reflected off all the tissue and stuff inside your body and all get focused back.
I get it. So
tumour.
you can work out what is getting in the way to scatter the light the way it is. If you reversed that, you'd get back to an original picture of what the light was like before it got scattered all over the place.
Yeah, and so it all gets focused back to where the light bulb is. The problem is...
Easy to say, tricky to do. How do you do that then?
Putting a light bulb in isn't exactly non-invasive, so you might as well chop the tumour out. Now, Zhao Zhu and colleagues at Washington University have managed to get around this problem. They focus ultrasound on the area of interest, and then they shine light on it whose frequency changes in time with the ultrasound. So the frequency goes up and down, up and down, up and down, up and down. They then look at the light scattering out of the body again. Then they use some clever optical tricks so that they build a hologram only from the light which is moving in time with the ultrasound.
That's amazing. So in other words, you use the ultrasound to make the tissue they're focusing on move a little bit. This will modulate or make the light waves stretch and shrink a little bit. So if you just look at the light which is stretching and shrinking a little bit, you know it's the bit coming just from the tumour.
That's right. And that means that you can then use this hologram to reverse the original light, and so you can produce a great big shot of light which then gets focused back onto the tumour or whatever you're looking at.
And what's the optical readout? What does the person who would be imaging the tumour, what are they going to see? Would it build a sort of 3D reconstruction on a screen for them?
Well, you can do various things. One of them is you can move the focus of the ultrasound, and then you can essentially sort of build a picture up of what it looks like to the laser light, and you can build a picture up using light, so that might tell you information you can't get from the ultrasound. You could also fill some with this photodynamic therapy type stuff, and then you could actually destroy the tumour where you're focusing the ultrasound on, or you could put some kind of fluorescent marker in the body which only fluoresces when something interesting is going on, and then you just look at the parts of the body which are fluorescing and do all sorts of beautiful, interesting things like that.
Can they see right through the body, or how deep can they go?
I've seen pictures from sort of 2 or 3 centimetres down, which is far better than you get conventionally.
Certainly is. Thank you, Dave. Now, if you're a big fan like me of eating oily fish, then you're probably doing your eyesight a big long-term favour, it turns out, because scientists at Harvard Medical School have discovered that the omega-3 fatty acids that are found in the fish can block the damage that's done to the retina by diseases like macular degeneration. They've found also the gene pathway which is responsible for this protective effect. And from Harvard, to tell us how it works, here's Lois Smith.
The problem that I have been trying to solve is one of what's called retinopathy, which is abnormal blood vessel growth in the eye. This occurs in 3 major diseases. In premature infants, in children, there's retinopathy of prematurity. In this case, abnormal blood vessels grow and cause retinal detachment. That is, the retina, which is the light-sensitive tissue in the eye, comes off the normal mooring and children go blind. In the middle-aged or working-age population, diabetic retinopathy causes the same problem. In the elderly population, there's a disease called age-related macular degeneration. There's also abnormal blood vessel growth, which can bleed and cause blindness. Taken together, these 3 diseases are a major cause of blindness.
And what are you doing to try to understand what unites them in terms of the pathogenesis, the way these diseases occur?
There are 2 parts. One is there's first loss of normal vessels that causes oxygen starvation, and then the oxygen starvation stimulates the production of chemicals that call in this pathologic or abnormal blood vessel growth. So I've been trying to understand basic pathways that cause this disease process, both vessel loss and then abnormal blood vessel proliferation.
And what's been the experimental method? What are you actually doing?
I've developed a method in mice, and in this model system, we expose mice to high levels of oxygen and then bring them out into room air. And the blood vessels in the eye first disappear and then come back, roaring back in this pathologic form. Because it's in a mouse, we can do genetic manipulation. And by doing that and then subjecting them to this oxygen, we can find which gene pathways are involved in the disease process.
And presumably also whether different treatments or interventions work and
Absolutely.
in what context? In other words, which gene pathways those treatments, which we know exist but don't yet know how they work, we get an insight into how they do work.
Absolutely, that's true. In this case, I was very interested in looking at omega-6 fatty acids and omega-3 fatty acids. So the omega-6 fatty acids are the kind that are found in hamburger, basically, and the omega-3 are found in fish or a Japanese-type diet. So we looked at the difference in these two diets to determine whether or not by changing the ratio of lipids that you ingest, whether or not that would have an effect on this proliferative disease, that is the production of these abnormal blood vessels.
Because if you look at the epidemiology, if you look at populations of humans, what they eat and who gets what, people who do have a fish-dominated diet tend to fare much better, and they're also at much lower risk of getting these retinopathies compared with people who are the hamburger eaters.
There's been one study in age-related macular degeneration that did suggest that, and we have been working with that group at the National Eye Institute to provide the fundamental scientific basis for that process. Yes, that's true. And in this study, what we're looking for is what metabolite, that is, what breakdown product really causes this beneficial effect, and what are the enzymes or what are the molecules within our body that create the breakdown product. Some of the enzymes are very, very commonly inhibited with over-the-counter drugs. That is, there's one that's called cyclooxygenase, or COX, and COX inhibitors include aspirin and ibuprofen. So these are drugs that many people take, and we wanted to be sure that the metabolic product that caused the beneficial effect was not blocked by taking something as simple as aspirin.
And put my mind at rest and tell me that it's not, please.
It's not. You can do both. You can take aspirin or ibuprofen and still take omega-3 fatty acids and have the beneficial effect of both.
Which is a massive relief given the huge contribution aspirin is making to saving lives from stroke and heart disease, and maybe even preventing Alzheimer's disease as well. But if it's not impacting on those pathways, what are these fatty acids doing to prevent people getting retinopathy then?
It's going through a different pathway that's called lipoxygenase, or LOX, and this pathway produces a specific metabolite called 4-HDHA, which provides the beneficial effects. And interestingly enough, one of these effects is through an enzyme called PPAR gamma, which is what drugs to help improve insulin sensitivity in diabetes also activates. So the implication of this is that by taking an increased level of omega-3 fatty acids, that we're increasing insulin sensitivity in diabetes as well.
So now that you know this, now you know the pathway involved, does this mean that you can prevent the depletion of oily fish in the sea that we love to eat to a certain extent by producing some kind of molecule which will be very targeted at this problem of retinopathy and can exploit the same effect?
That's exactly what we're interested in pursuing next. And yes, that's our hope and expectation. Although it may still be better, instead of depleting the fish in the sea, to have algae make the omega-3 fatty acids that we can still take. It may be simpler to take the precursor than it is to take the metabolic product. But I think we can do it without depleting fish.
Can algae do that? How easy is it to get the algae to do what the fish do for us at the moment?
Actually, they are the original source because algae produce it and then the fish eat it, and we then eat the fish. So it's quite simple to have them do that.
I think I'll stick with the oily fish. I think it's probably tastier than eating the algae. But fascinating, I just did not know that the essential omega-3 fatty acids come from algae, not the fish. That was Dr. Lois Smith. She's from Harvard Medical School, and she published the work you've just been hearing about in the journal Science Translational Medicine this week. Diana.
Fascinating stuff. Well, this week, scientists in China have identified an environmentally friendly way of making acrylic acid. Typically, acrylic acid is derived from propylene, so ultimately it comes from crude oil. And over the years, it's become a very important industrial material used in everything from paints, glues, fixing treatments and textiles. More than 1 billion kilos of the stuff are produced each year for industry. Now, Wei Ji and colleagues at Nanjing University have found an efficient way of making it from lactic acid, which most of us know as the acid which makes your muscles ache during exercise. But lactic acid is a better starting material than propylene because it can be readily made by bacteria in huge vats, eating biomass. So, reporting in ACS Catalysis, G and his team have cited a new catalyst which allows lactic acid to be converted into acrylic acid at low temperatures. And if you can promote this reaction at low temperatures, then it means less energy or less expense is required to keep the reaction going. Now, they call the catalyst an NAY zeolite, which is because it's a Y type, and it's called that because of its pore size, sodium absorbent. Now, cat litter is also an example of an absorbent zeolite.
It's not a catalyst, though, is it? Or is it? I don't know. Neutralising nasty nifs, perhaps?
Well, some types of I can't say it now. Diatomous cat litter is actually a kind of catalyst, and it absorbs the wee. And during this two-stage process of the NAY zeolite, what it does is to dehydrate the alcohol from the lactic acid, that's C3H6O3, and it produces acrylic acid, which is C3H4O2. And the zeolite in this case has pores which can hold and exchange sodium cations in solution. Now, they actually add some alkali phosphates and reactants to the mix to get it going, but what they think is happening is that the catalyst helps release a proton from the lactic acid and helps it react with the reagent, producing acrylic acid. And it's got quite an impressive yield as well, of about 58.4%.
Big step forward. So now we can have more acrylic costumes for you to wear in the office, Diana.
You wish.
Well, here's a way to take some of the pain out of the rehab that people should have if they have a heart attack or cardiac surgery. The UK government has set a target of 75% of people should, if they have a heart attack, come to a series of rehab sessions afterwards, because this sort of intervention can help people to regain their confidence after they've had some kind of cardiac event. It can also help to intervene in lifestyle factors that can minimise the risk of having another heart attack, and therefore, all told, it can make a significant improvement in terms of people's quality of life afterwards. The problem is the attendance is deplorable, is about 30%. And this is not just a problem in this country. All over the world, we see this in countries that offer these kinds of rehab opportunities. And in some countries, it's largely because of geography that this happens. If you look at countries such as Australia, where people may live in the middle of nowhere, access to a hospital where these things are usually offered is not trivial. And there's a researcher at the University of Technology, Queensland University of Technology, that's Charles Warringham. And I spoke with him this week because he's published a lovely paper in the journal PLOS ONE, in which he outlines a strategy they've developed to use smartphones, which have been reprogrammed, to help the person do their rehab out in the community. And how it works is that they've taken some smartphones, they reprogram them so that they run software, so they can connect a heart monitoring pad up to the phone, and it also uses the GPS system built into the phone. And when the person then does their exercises, the cardiac trace from the patient, and they've tested 7 patients so far, one of whom was a country and western singer who couldn't actually attend the rehab because he was on tour at the time, but the data from each patient is beamed back in real time to the lab, where a technician who's trained in monitoring what the tracings are supposed to look like is able to follow the person's heart response to their exercise, because they can see how much the person's moving using the GPS. And what they found is that people found this extremely useful. They got equivalent scores in terms of people's improvement in fitness, lifestyle changes, depression scores, and their sense of well-being, compared with people who do actually go to the hospital-based sessions. And the patients loved it because rather than sitting on a boring treadmill or exercise bike in a room indoors in a hospital, they're actually doing this out in the street. And they're saying that this could be rolled out much more widely rather than just the 7 patients they've done, because the software is not hard to write for the phone. But also, by using other functionalities built into these phones, like the accelerometers. This is the way of measuring whether they're tipped left and right, so it knows which way to show you the picture on the screen, for example. You can use the same technology in the phone to work out how a person is moving. So if you've got a person who's had a stroke, you can analyse their gait and how well they're walking. And therefore, you can give them physiotherapy advice remotely. So it's a really good way to reach people in the community without having to drag them into hospital, which I think is a terrific use of new technology to move the world forward. Actually, incidentally, there is a longer interview with Charles Warringham. If you want to catch up and listen to him talking about this, it's at thenakedscientist.com/specials. If you look up Charles Warringham's thing there, you can listen to him talking about it.
Now for something a bit different. New, thinner, more flexible superconducting cables have been developed. Superconducting materials are materials whose electrical resistance drops to completely zero when they're cooled far enough. There are two major different types. There are low temperature superconductors, which work below about minus 263 degrees Celsius or 10 degrees above absolute zero. These are often conventional metals and they're easy to bend, but you need immensely good insulation and liquid helium and things to keep them cold, which makes them very, very impractical for anything other than something like an MRI scanner. And then there are high temperature superconductors, which can work up to around 77 degrees above absolute zero, which is far easier to achieve. It's liquid nitrogen temperatures, which you slosh around in physics labs all the time. These would be ideal for carrying current, but unfortunately they are all brittle ceramics, so similar physically to a china teacup, which makes making cables out of them very, very difficult.
They're not going to bend easily.
They're not going to bend easily. The only way to make them at all flexible is to use incredibly thin pieces of superconductor, which makes them just about flexible enough. Despite this, most superconducting cables are still so brittle they have to be wound around large formers, sort of meters across, make them very, very difficult to feed through some kind of tubing or ducting anywhere you want to install them. Now, Danko van der Laan has improved this significantly by using a slightly different superconductor called gadolinium barium copper oxide, or GBCO, whose superconducting properties are no better than the other standard IBCO, but it degrades much more slowly when it's bent slightly. This has allowed him to wind the superconducting tapes around a copper former that's only about 6 millimetres in diameter. This means the cable can bend around much smaller circles. They've managed to successfully bend it around a diameter of about 25 centimetres, while still being able to carry a current of 1200 amps.
Gosh, that's a lot. So would this work then if you were to industrially try and apply this? So you've got this material now which will bend around corners and things. So would you use it by putting it in another tube that could carry, say, liquid nitrogen to keep it very cold? So you'd have a very small cable but capable of carrying an enormous current, but it would have to be ensheathed in something that was capable of being very cold.
Yeah, that's right. You then have to put some liquid nitrogen pipes around it and then possibly some insulation around it. But in liquid nitrogen pipes and insulation can all be made flexible, so that's not a major problem. Just this single cable is carrying out about half the power of one of the big, huge 400 kilovolt cables. So it's a really serious amount of power you could put through this if you insulated it well enough. And this could possibly make it practical for installing it in things like ships or aircraft, which the US military is very interested in, so they can make their ships electric powered. So you have a huge generator, and you can still use quite thin cable to get down to a big, possibly even superconducting motor underneath, which saves lots of weight and means your ships are a lot faster.
And if you'd like to read up on anything else we've covered so far this week, the references and transcripts for each of the news stories we've discussed are online, and they're at thenakedscientists.com/news.
Reacting to the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with me, Chris Smith, also with Diana O'Carroll and Dave Ansell. Our email address here for the programme, chris@thenakedscientist.com. Sophie's got in touch. She's in Southend. Hello, Sophie.
Hello.
You have a very interesting, if not slightly damp, question for us. Go ahead.
My question is, if you put a shower head over the top of a 2,000 feet high up cliff, would the water fall to the ground or would it evaporate?
Is this something you've sought to try yourself, Sophie, at some point? How did this question pop into your head?
Well, I've been thinking about it for quite a while and it just came into my head.
Well, let's hope that a man who's got the answer in his head is Dave. Go on, see if we can help Sophie.
Well, to start off with, I didn't have the answer in my head, so I thought I'd do some science properly and actually do an experiment. So in the office last week, I had I got a lemonade bottle lid and a set of very accurate scales, and I rigged up a fan next to it because I figured that we're interested in how fast the water is evaporating. If the drops of water from the shower head evaporate before they hit the ground, then they're not going to hit the ground, but if they get all the way down there, they will. So I got some water in this lid. I put a fan across it. The fan probably wasn't really powerful enough, but it gives us a general idea of what's going on. And I ran it for about 10 minutes. And in that time, about half a gram of water evaporated.
So that's half a mil?
Yeah, so half a millilitre of water. And that was for a 28 millimetre diameter lid. If you work that all out, it comes out that you lose about 0.1 cubic millimetres of water per minute per square millimetre of water.
So extrapolating that to Sophie's shower head going over the cliff.
Okay, so then I worked out the area of a raindrop, of different size raindrops, and worked out how long they'd take to evaporate. So probably a normal large size raindrop is about 6 millimetres, so that's probably what you're getting from the shower head. But if you do work that out, it'd probably take about 18 minutes for it to evaporate.
How long does the raindrop really take to fall 2,000 feet over a cliff?
Its terminal velocity is about 10 metres per second, so it'll probably take 70 seconds.
So what fraction will evaporate then?
A tiny fraction, maybe about an 18th of it, about a 20th of it will evaporate.
But not zero. I mean, there is an evaporation. Because there was a paper in Nature a couple of years ago where they were using oxygen isotopes to work out how much rainfall evaporates when rain falls from the sky. And something enormous, like 40 or 50% of the rain that falls, doesn't ever make it to the ground.
I could quite believe that, because I then thought I'd do some other calculations and work out what happens if you have a smaller droplet, because from a shower head you get the big droplets coming out of the bit, but you also they kind of break up into small ones. And around about 1 millimetre diameter raindrops falling off a 2,000-foot cliff, they'll probably just about evaporate before they hit the ground if the air was about the same as in our office, which is not necessarily a good assumption.
I'm not sure that's a good idea at all.
It'll depend on whether you're doing it in a desert or if you're doing it in Scotland when it's raining already. So it very much depends, but certainly the small ones could evaporate depending on the weather.
There you go, Sophie. So if you have a very fine shower, then a significant proportion could evaporate, but if you've got a really good quality power shower with big drop sizes, then a very small fraction of the water will evaporate on the way down.
Okay.
All right?
Yeah.
Nice to have you on the show anyway. Thank you. Great question.
Thank you.
All right,
Thank you.
This is The Naked Scientists. Chris Smith, Dave Ansell and Diana O'Carroll. It's our science phone-in extravaganza, so if you'd like us to tackle a question for you, now's the time to send it in. chris@thenakedscientists.com is the email address. We have got Jeff, who is with us. Wants to talk about oil. Hello, Jeff.
Hey, guys. How are you?
We're very well, thank you. Where are you listening to us, then?
I'm listening to you from America, New Jersey.
So what can we do for you?
Yeah. Okay. First of all, thanks for this great podcast. You guys always have fascinating topics. My question for you, I've had this question for a long time, is when we pump billions and billions of barrels of oil and natural gas out of the planet's crust, are we destabilizing the Earth above by leaving these massive voids?
Okay, well, that's a really good question. And it's one that actually we've also had from A.D. Yates, who said, what do we replace pumped out oil and gas with? And I guess I can probably help both of you in one go here. The answer is that many people, myself included, a few years back when I first started doing all this kind of thing, I thought that, oil existed underground in these big open caverns, almost like a coal seam, and you take the coal away and you're left with a big cave. Well, actually, the best analogy I can think of to explain what it's really like is to imagine sticking a straw into a sponge and sucking water out of a wet sponge, because that's essentially what the conditions are like underground. When the oil was formed, it was lots of marine creatures and other organic matter got compacted on the seafloor below layers of sediment, and the huge pressure heated everything up and cooked all these dead creatures into the soup, which became crude oil that we extract today. But that means that what that material is trapped inside is a porous rock. And I have to acknowledge on our forum, nakedscientist.com/forum, we had an answer to a similar question a couple of years ago, which a geologist on the forum, Jim Bob, gave a very elegant answer to. And he points out that if you look at the rock that an oil well is drilling into, the porosity of that rock, in other words, the proportion of holes, is about 13%. So in other words, if you take the cross-sectional area that's holes as a whole proportion of the cross-sectional area of a piece of rock, about 13% is just empty space in the rock, and that empty space is filled with the oil. Now, he also says that that is about the same open porosity as concrete. So in other words, when you take the oil away, you're left with something which is equivalently strong already to concrete. So you're not leaving a big space, you're just taking the oil out from between all these little holes, which are to a certain extent in continuity. But then the next point to bear in mind is that this oil and gas that's underground is under extremely high pressure. And that means that as you take the gas away, largely under its own pressure, or the oil, then other things will move in to displace it. And so therefore some water will move in from the adjacent rock and will also take up some of the space that's been vacated. And in fact, when people call a well spent, in other words, they say that an oil well has become empty, actually, the amount of oil that's left behind can be as much as 90%, because the oil is very hard to get out. And to come back to Adie's question, what do we replace it with? Well, sometimes you can help to get the oil out by pumping something else into the porous rock, such as water, to help the oil be pushed up to the surface because it floats on the water. The Norwegians have got a technique where they pump steam in underground, and the steam, being hot, can make the oil become runnier, so it's more likely to consolidate, join together into big blobs of oil, which are easier to get out. And also, as Dave pointed out earlier when we were discussing this, sometimes they also put surfactants, things like washing up liquid, down underground, and that helps the oil to have a lower surface tension so it can flow out of all these little holes more easily. So the bottom line is you're sticking a straw into a sponge. The porosity of that sponge is equivalent to concrete, so it's still very tough rock underground. Therefore, you don't get left with a great big gaping hole, and therefore there are probably very few seismic consequences as a result. But a great question. Thanks for joining us here on The Naked Scientists. Diana, I've got one here for you, and I like this question very much. Peter Rubinelli says, and this is highly topical, what is El Nino? He says, thank you very much for your excellent science show. I've got a question. What is El Nino, and how does it affect the jet stream, if it does?
Okay, well, El Nino is usually defined as having occurred when you get a high air surface pressure on top of the Pacific Ocean, and the actual surface of the Pacific Ocean increases in temperature. And what happens as a result of this is you get the Humboldt current, that's the sort of nutrient-rich cold current of water, moving, and it moves away from the coast of South America. So that takes away all the nice happy fish, and it means that all the fishermen in South America lose a lot of their stock. And it also causes quite heavy rain and flooding in the southern part of America. And conversely, you get drought and sometimes even bushfires on the sort of eastern side, so where Australia is, of the Pacific. And this kind of thing can happen roughly every 5 years on average. But as for the jet stream, we don't really sort of know for sure, but it looks like El Nino can pull the polar jet stream slightly further south, which means that North America can suffer maybe more rainfall, maybe a bit more snow, colder winters. But we don't really know if it actually affects Europe, possibly.
OK, Dave.
I guess also that essentially you're changing the temperature of a great big area huge area of the Pacific Ocean, which will affect which area you're heating the air up above. So it'll change the kind of global circulation of air currents slightly, which have all these knock-on effects.
Exactly. It's a huge system and a hugely complex system as well. And some people have even recorded maybe more droughts occurring in Africa during El Nino event, which is, it's the other side of the world.
Indeed. Thank you very much, Diana. This is The Naked Scientists with Chris Smith and with Dave Ansell and with Diana O'Carroll. And Emma Harrison is on the phone for us. Hello, Emma.
Hi, the question I would like to ask is, does increasing the concentration of a reactant speed up an experiment? And is this more than increasing the concentration of both reactants?
Is this for your homework at all?
No, it's just I've been doing science coursework, and then this was a question that came up that I didn't have to answer.
And I'm just saying, if we get you an A, you have to share the winnings with us, OK? All right. Dave, what do you think?
A reaction is normally to do if you're reacting two different substances together, so a type of molecule called molecule A and molecule B. If we just think about one molecule of molecule A, if you have a great big vat with only a few molecules of B in it, molecule A is going to wander around gently throughout this huge vat, and because there's hardly any molecules B in there, it's almost never going to meet a molecule B. So it's very rarely going to react, so it's going to have a very, very slow rate of reaction. If you've got loads and loads of molecule B, say billions and billions of in there, it's hardly going to have to travel any distance at all. So the time it takes for a single molecule of A to react is going to be much, much less. So the greater the concentration of B there is, the higher the rate of the reaction. Similarly, of course, the more A there are, the more times it is happening at once. So the rate of reaction is going to increase. So in general, the total rate of reaction is related to the concentration of molecule A times the concentration of molecule B.
Dave, thank you very much. I hope that helps you out, Emma. Good luck with your coursework. What else is on the syllabus?
Just molecule structure and atoms and things like that.
We're back with another Q&A show in a month, so if you've got any more queries, then see if we can help you then, OK?
OK, that would be great.
Perfect. Thanks for calling. Quick question. Hydra in Cambridge says, Dr. Chris, did you manage to have a word with your friends about cranberry juice if it's best for water infections? Cranberry juice is very good for preventing and treating urinary tract infection. The reason for that is that there is a chemical in cranberry juice which downregulates on the surface of cells which line the urinary tract, in other words, all the way from the kidney right out to the outside world. It turns off on the cells that line that pathway a molecule which is a mannose sugar linked to some other bits of protein, which E. coli, the commonest cause of urine infections, like to cling to. So if you downregulate the expression of that chemical on the cell surface, it gives you anatomical Teflon. It makes you very slippery inside, so the bacteria can't cling on, and as a result they're more likely to be washed out every time you have a wee. And so therefore cranberry juice is very effective at reducing either the initial occurrence of a urinary tract infection, but also it's very good at preventing it coming back or treating it as well. Diana, here is one for you. This is a reaction to your apes question. S. Mason via Twitter says, "We do not evolve from apes. The species you spoke about died out thousands of years ago and they have different DNA." He also goes on to say, "If we evolved from apes who all have brown eyes, then where did blue-eyed humans come from?"
All right then, so I would say that actually, yes, we are all in the same family of apes. Now, a common misconception is that people will say that we evolved from, say, the chimpanzees or the gorillas, but of course that's not true. We coexist with chimpanzees and gorillas who are also apes, but we have a common ancestor that existed several million years ago. Now, the species I spoke about was Australopithecus afarensis. Now, that lived sort of somewhere between, I think it was 3.7 and 2.9 million years ago, and almost certainly had quite different DNA to us. But then again, humans have different DNA to each other, and there's no way we can actually measure what the differences of DNA between ourselves and afarensis would have been, because of course they're fossils and there's not going to be much DNA sort of left hanging around there, I don't think. As for the blue eye adaptation, I believe that mutated sometime around 10,000 years ago, and of course that mutation would have occurred in northern European farming populations almost certainly.
I mean, to add to this, we've got the whole point that, because he makes a thing about eye colour, why don't we look at skin colour? Because chimpanzees and extant apes have pale skin. If you go back 6 million years to the ancestor we last shared with them, that also had pale skin, but the earliest generations of humans had dark skin because they were hairless and therefore needed to evolve some kind of protection against the sun. When they then leave Africa and come up to northern latitudes, and low latitudes later obviously, then they re-evolve to have paler skin, because if you have that dark skin up here where the sun don't shine very often, you don't make enough vitamin D and your bones suffer, and there's insufficient sunlight for the loss of folic acid, which is the reason to be dark in Africa, for that really to be a problem.
Exactly, and this whole thing hinges on mutations, on people giving rise to new generations of people who are slightly different. And so inevitably you are going to get people with different shades of skin and different eye colours. It will happen eventually over a long enough period of time. And
the evidence of that, just look at how different humans are across the whole surface of the Earth, from one geography to another. And there's the evidence that we're extremely genetically diverse and we're all the same species. So add a few more million years into the mix and anything could happen.
Who knows what we'll all end up looking like.
Even explain why you look the way you do.
Hey.
Just beautiful, beautiful.
Harsh, Chris.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists. It's Chris Smith, Diana O'Carroll and Dave Ansell. We're answering your science questions for you this week, so do send them in. It's chris@thenakedscientists.com if you'd like to get them in by email. Our Twitter address @nakedscientists. In London, blue plaques have been placed on buildings across the city for over 140 years to highlight where notable people in history have lived. This week, Meera Sinthalingam went along to the unveiling of just such a plaque for a scientist whose work actually changed the field of chemistry.
I've come along to the chic area of Notting Hill in London, and more specifically to number 12 Arundel Gardens, where the home of chemist Sir William Ramsay is being honoured with an English Heritage blue plaque. Now, as the bagpipes may suggest, Ramsay was a Scottish chemist, but he was also a Nobel Prize-winning one. He was awarded the prize for his work finding a new group of elements to be added to the periodic table. These are now known as the noble gases. These are a group of odourless, colourless elements that are mainly known for their lack of reactivity. And now joining me here at number 12 to tell me a bit more about Ramsay's work is Alwyn Davies, Emeritus Professor at University College London.
Previously in 1862, Mendeleev had classified all the elements into a very neat table And Ramsay's gases he formed, he prepared, didn't fit into that table. He added a whole new group to it. So from the fundamental chemical point of view, it was really world-shattering.
What do we know then about Sir William Ramsay as a chemist, say at UCL, where he was chair of inorganic chemistry?
His big characteristic was his devotion to practical work. He was a hands-on man. He wasn't a theoretician. He taught himself glass blowing. He designed and built his own apparatus. He was prepared to tackle problems which other people would be just too scared to do. He finds two of the rare gases, helium and argon, and he guesses there's something in between. Now he says here's a supposed inert gas, and the whole world to find it in. He does look in the whole world. He goes to Iceland and looks in the volcanoes. He goes down to the Pyrenees. He gets meteorites and powder seas and gets the gases from them. He looks for 3 years to find something that might not exist. Now that's the thing that most people would be too scared to do. From the more practical point of view, for magnetic resonance image scanning, you need liquid helium, one of his gases, to get the strong magnetic field that you need. For doing much chemistry, you need an inert gas to stop the air reacting with the chemicals. For that, you use argon. Argon goes into double glazing between the two panes for good insulation. Xenon ions are used for propelling spacecraft. Despite their chemical inertness, or maybe because of it, they do have many uses.
I just wanted to say a few words about what is quite clearly one of the most familiar and best-loved signs of London's streets, which are the blue plaques.
The Blue Plaque scheme is currently run by English Heritage, and the historian that researched the case is Dr. Susan Sked.
The Blue Plaque scheme was started in 1866, founded by the Society of Arts. English Heritage has actually only been running it for the last 20 or so years, and the scheme was inspired by the need to preserve some of the historic houses around London that were being torn down. So to begin with, the scheme was about saving historic houses as well as commemorating the homes of notable people. It's not just about the person, it's about their former home or workplace. And that's why placing a plaque for Ramsay is so important, because it was here that he achieved his greatest works, really.
So where does William Ramsay fit into all of this? What makes his home here in Notting Hill appropriate?
Well, William Ramsay was an outstanding chemist. He won the Nobel Prize for Chemistry, the first Briton to win that prize in 1904. He discovered not just one, but 5 of the noble gases and really completed the periodic table of chemical elements.
Shall we do a countdown? 5, 4, 3, 2, 1. Hooray!
As well as Professor Davies, another organiser of today's event is Dr. Andreas Seller, also from University College London. Andreas, another interesting aspect of today's event is the fact that you've also managed to round up a group of cyclists and are yourself kitted out in your cycle gear upon a Brompton bicycle.
Well, it seems kind of crazy. What's this got to do with the noble gases? Well, in 1887, Ramsay wrote to his sister, in sort of breathless with excitement, saying, I go to college on a bicycle. And you think, well, who cares? But if you think about it, the safety bicycle had only been invented a couple of years before. In fact, this is the year before Dunlop invented pneumatic tires. So he was really on the cusp of new technology. And he claimed to be able to cycle from home here in Notting Hill to college in 18 minutes. Now, the streets were cobbled. He was using solid tires. I mean, this would have been an incredible achievement.
Are you all attempting to race his 18 minutes? So today, the journey from here to UCL involves going through Oxford Circus, so lots of traffic lights?
I think today, really, we're going to be taking the scenic route, and actually we'll be pointing out along the way other people who lived in the area. There were people like contemporaries like Sir William Crookes and so on. Going to take it quite easy.
You've really drawn attention to the area of chemistry and chemists like Sir William Ramsay today, as you've managed to bring together scientists, historians and cyclists all to one place.
I think this really tells you about how deeply chemistry permeates our lives. In fact, modern bicycles rely hugely on chemical technology. Whether you're talking about lube, whether you're talking about brake pads, just the alloys, right, that make up the bicycles themselves. It's all chemistry.
Well, I better let you get off, and all the cyclists are waiting for you.
Gather together and get the marshals.
And getting to UCL took them 40 minutes, so a little bit slower than Ramsay's time. That was University College London's Dr. Andreas Seller, and before him, Dr. Susan Sked from English Heritage and Professor Alwyn Davis, also from University College London. They were talking with our own Mira Senthilingam. John Charlton says on Facebook, nakedscientist.com/Facebook, Dave, what keeps jets in the air? Is this pressure differentials or force from the air or some kind of combination?
Okay, I guess as in jets and a general aeroplane. Essentially, when an aeroplane moves through the air, if you've ever tried to walk from the back of the plane to the front of the plane, you'll have noticed it's always uphill. There's an awful lot more uphill than you're expecting. That's because the nose of the plane is pointed upwards, so the wings are pointing slightly downwards. This means that when air hits them, both underneath it just gets deflected, bounces off and gets deflected downwards a bit, and also due to an effect called the commander effect, the air on the top of the wing tends to stick to it and it also gets deflected downwards. So the wing is pushing air downwards, so Newton's laws mean that every action has an equal opposite reaction, so the air is pushing the wing upwards and the plane stays up.
I'm glad you explained it like that, because Ben and I went to see some people at Rolls-Royce who make aeroplane engines last week, and they said one of their interview questions is to ask their would-be material scientists who want to work on their engines, how does an aeroplane fly? And they asked me, and I gave the answer you gave, and I said, I hope that's right. I'm talking to Rolls-Royce here, and they said, actually, yep, that's the kind of answer we look for, and the majority of people don't actually give it. So if you're going for an interview at Rolls-Royce, that's what you've got to say, what Dave just said. Now, Chad is on the line with a question about snot. Hello, Chad.
Hello. Oftentimes when we have colds or sinusitis, we produce green mucus. I was wondering, do the mucous membranes produce the mucus green, or does it turn green in our sinus cavities?
Yeah, we've all had those really nasty colds where the stuff you're coughing up, and you can almost chew it because it's so thick and horrible, isn't it? And it's a lovely vivid green colour. I actually had a patient who had a very bad pneumonia, and I said, are you coughing anything up? And she said, oh no, and then proceeded to produce this huge blob of literally bright green stuff in front of me, and she really had quite a bad pneumonia. This is actually your body making this stuff. Mucus in health is colourless, and it's produced by little cells called goblet cells, which are in the epithelium, the layer which lines your airways, and this is rich in a protein called mucin, and when they secrete this substance over the surface of your airways, it attracts water from the surroundings and swells up and becomes much more voluminous, maybe 600 times it swells up by as it gets more water into it. And it's very sticky, and its job is to trap microorganisms, pathogens, bits of dust and debris, that kind of thing. So it's a sort of cleaning thing. But when you get an infection, the infection can be viral or bacterial, and the infection will damage the cells that line the airways, and the damage to the cells is intentional on the part of the pathogens. In the case of viruses, because they want to grow in the cells, and in the course of growing in the cells, they kill them. But in the case of bacteria, the bacteria kill cells because if they kill the cell, then all of the goodies inside the cell, the raw materials, can be liberated, and the bacteria scavenge them and use them themselves. But in the course of doing that, they create quite intense acute inflammation, and this releases various inflammatory mediators which attract the immune system to the area, including a class of cell called a neutrophil. And these neutrophils have something called a respiratory burst, and what that means is they produce enzymes which produce free radicals of oxygen. And these free radicals of oxygen destroy the bacteria, but in the process they can also kill the white blood cell. But these myeloperoxidase enzymes that make this respiratory burst contain iron as a cofactor. And it's the compounds of iron which are present in various oxidation states that give the mucus its bright green colour. So healthy mucus isn't coloured, but when there's an infection going on and there are lots of white blood cells there which kill themselves with this respiratory burst, then the mucus gets this lovely, vivid green colour. Yum. So that's the answer. Dave, got this one here. Alex says, how does magnetism multiply? If I stick two bar magnets together, do they pick up more paper clips than if I had just one bar magnet acting in isolation?
They will pick up some more bar magnets. If you have a single bar magnet, essentially a North Pole and a South Pole, and the force applied by those essentially reduces with the inverse square, so if you double the distance, the force goes down to a quarter. However, because the North Pole is the opposite of the South Pole, if they're very, very close together, then the North Pole is effectively reducing the strength of the South Pole and vice versa. And so if you get very, very close, it will be weaker. If you make the bar magnet longer, then effectively you move the North Pole away from the South Pole, so they cancel each other out less. So essentially, especially if you start off with a reasonably long bar magnet, it's not going to make very much difference to the strength of the magnetic field right next to the end of the magnet. A little bit, but not very much. But it will drop away much more slowly with distance. And so, especially for the paper clips which are dangling quite a long way away, that might have a significant effect. For the ones which are close to the end of the magnet, it's going to have hardly any effect at all.
Thank you, Dave. Bernie in Peterborough says the young lady's shower question was absolutely fascinating, although surely the amount of water that gets to the bottom depends on the temperature of the air at the time. In other words, the warmer it is, the more will evaporate.
Yes, totally. All my calculations were based if it has to be falling through the air in our office. So yes, it'll be very dependent on the temperature and the humidity and where you're doing it.
Good point. Thank you, Bernie, for that. Diana.
Right, now here's a question. What colour are dinosaurs? It's an issue that's puzzled paleontologists since fossils of the creatures were first discovered. But now, thanks to modern science, dinosaurs are beginning to show their true colours. Professor of Paleontology at the University of Bristol, Mike Benton, showed Planet Earth podcast presenter Richard Hollingham a fossil of a 125 million year old bird.
So we have some specimens here.
So you're opening a locked cabinet and pulling out a drawer here. Now this
is an astonishing
this sample fits in about the palm of your hand.
Yes, palm of my hand, and this is a complete little bird. And you can see that the bones are a kind of cream colour and almost chalky in appearance, and these are the wing bones here. Here's the backbone and the ribs there. And I think, yes, here's the head kind of bent back, almost over the top of the thing. And around it is a halo of fluffy, bluey-grey material, which are traces of the feathers. And you can see at the edges they become wispy. And so we were then focusing on this dark grey material, which is obviously remnants of soft tissue.
It is coloured. There are different shades of brown and grey. Can you say that they were the colours of the feathers then?
No, I think that's been the question so far. There are many fossil birds and now many fossil dinosaurs with rather obvious feathers around the edge. And nobody can deny that they're feathers because in many cases they have the detail of a wing feather with a quill up the middle and the branching barbs at the side. Others, like these ones here, are the sort of wispy down feathers, as we would call them, that cover the whole body area and the base of the wings, and are there mainly for insulation. But as you look at them, the differences in tone, the different shades of grey, you would be foolish to try and interpret those as original colour.
So you've got some of the samples that you put under the electron microscope. We can hear this electron microscope buzzing away behind us. If we look at the screen here, you've got one of the images when you're zooming in to sort of micron level,
so this
level
scale
here.
Is 2 microns.
And it's almost like a series of little rugby balls all jammed together.
Yes, they're sort of arranged higgledy-piggledy. You can't see particular rows. These little structures, judging by their shape and size, we're pretty certain that these are what are called melanosomes. Melanosomes in feathers of modern birds are introduced at the very early embryonic stage of the feather as it sprouts from the skin. And they come from the skin itself. So melanin is a well-known chemical that occurs throughout almost all organisms. Mostly it gives a black colour. And in the case of birds, it is produced within the skin, and then it is packaged in a particular way before it goes into the feather, because the keratin that makes the feather is rather like a plastic, or it's quite hard, solid material, and in order to get the chemical in, it has to be packaged into these organelles.
So a particular shape gives you a particular colour. Is that what you're looking for?
This is what we're looking for, and it is a remarkable fact that across all modern birds and across, indeed, all modern mammals, there are two main kinds of melanosomes, and there are numerous others in between, but the two main end members are a sausage-shaped melanosome that's about 1 micron in length, and at the other end is a spherical melanosome that's about half a micron across, or just slightly less. And these two end members always correspond to black and ginger. So the long sausage-shaped one is black to dark brown and is called a eumelanosome, and the spherical one at the other end is a ginger colour, always in mammals and birds and the rest, and is called a pheomelanosome.
So let's zoom back out from these samples you've got at the micron level under the electron microscope to this dinosaur bird. What does it look like?
We looked at a number of different dinosaur specimens from China, but the one we were particularly keen to study in detail is called Sinosauropteryx. And it was a small turkey-sized animal with a long, thin tail. But the reason we chose it was because it has the most primitive feather-like structures. And we thought if we can not only determine the colour, but also determine whether these are feathers or not, then we're doing something important in terms of the evolution of the group. So we had two things to do, and we looked at some of the dark-coloured ones and found that they were full of pheomelanosomes, the ginger-giving melanosomes. So we believe this shows two things. First of all, that these simple bristle-like filaments actually are some kind of a feather, and that's important. And secondly, they happen to be ginger. So we can reconstruct this dinosaur at least with a ginger and white striped tail, like a barber's pole.
Dinosaur or dinosaur?
Ginger power, yes. Revealing the coloration of dinosaurs millions of years after they died. That was Mike Benton from the University of Bristol, and he was talking to Planet Earth podcast presenter Richard Hollingham. And you can find more at thenakedscientists.com/Planet Earth.
If you'd like to get in touch with us, email chris@thenakedscientist.com, tweet @nakedscientists, or join us on our Facebook page. You can find that at thenakedscientist.com/Facebook.
Now, Dave, I'm glad you're there, because it's time to do your bit. You got a balloon, which I whacked across the studio at the beginning, but what's all this in aid of?
Okay, if you throw a balloon gently, it just kind of behaves as you'd expect.
Yeah, straight line, yeah.
It just sort of moves in a straight line, it slows down slowly, just as you'd expect. But if you whack it really hard, something strange happens. This is always going to go horribly wrong.
So you want us to watch what's going to happen, okay. It's quite quick. Can you do it again?
I'll do it again.
Okay. I think what I saw was the balloon going straight for quite a long while and then suddenly, all of a sudden, going off course.
Yeah, I spent a long time thinking about this. I was trying to work out what's going on, and I've done it with a high-speed video camera. You're not making it up. That is what's going on. I also spent a long time this week with a smoke generator, a load of balloons.
Been to your dodgy nightclubs again?
It was actually in the back of my garage. It was all a bit odd. There's videos on the website at thenakedscientist.com/kitchen science. And what seems to be happening is when you hit the balloon really, really fast, it sort of drags, or possibly actually even is pushed by a load of air moving behind it. And actually that air moving behind it probably has more energy than the balloon does itself, because the balloon is so light. And so it keeps on going for a long, long time until this arrangement gets unstable, at which point the balloon sort of falls off that air, and actually the air has some of the properties of a smoke ring. A bit like that, you've got air going on the outside and moving in forwards at the back and backwards on the outside. So when that the air moving behind it overtakes, it kind of pushes the balloon off the side, sometimes actually even pushes it backwards, and the balloon suddenly stops or jumps off in a strange direction.
Okay, so you've explained why it happens, but why does the air behave in that way in the first place? Why doesn't that happen with, say, a football?
Related things do happen with a football. You get strange transitions with a football. Something related is that the drag on a football increases as you'd expect as it gets faster and faster and faster. And all of a sudden, above about 20 metres per second, it suddenly drops. And that means that if the football hits the ball incredibly hard, it will go very, very fast. And then as it slows below 20 metres per second, it will suddenly slow down. And also, if they're spinning it, it will suddenly start to grip the air. And it will suddenly change direction and confuse a goalkeeper.
So when it slows down, it gets hold of the air better, and then you get much more resistance to the trajectory of the ball, so it will feel a lot more of a retarding force and slow down more dramatically or change direction, and that's what confuses the goalie.
Yeah, of course, with a balloon, the effect is hugely stronger because the balloon's so light compared to the air, which is moving past it.
So apart from football, are there any other real-world examples of this bit of physics in action?
I guess pretty much all ball sports, you're going to have similar kind of effects. Certainly ping pong balls do something very, very similar. When I've accidentally shot them out of the top of electrolysis rigs at about 100 miles an hour, they've behaved very, very strangely.
Yes, I think I remember that. About 5 years ago, you actually detonated this bomb, and the Vice-Chancellor of Cambridge University was standing there, and she thought someone was trying to kill her. Shoot her or something, because there was this enormous explosion. It was you electrolysing water and blowing it up. Diana, Klaus Gauffin, I presume that's how you pronounce his name, he says inbreeding is a very bad idea from an evolutionary point of view, because it leads you to think about various powerful mechanisms that could have been evolved to limit it happening, because obviously you get bad genes cropping up in populations. So what do wild animals do, he asks, to avoid incest?
Yeah, well, there's a few adaptations. I mean, one interesting one is hyenas, and apparently female hyenas will only breed with males that have been recently born into their group or who have just recently joined it. And the male hyenas will only move to new groups of females to breed. So they've got a sort of social setup which helps to avoid incest. But on a more sort of scientific level, lemurs actually use scent, they use pheromones on their naughty bits, to detect who is is the most closely related to them and who is the furthest sort of relation. And it's the females will actually smell the males and decide, actually, he seems like perhaps a bit of a close relative. I'm not going to go there. But I think, Chris, isn't there also something about mice?
Well, mice is intriguing. The explanation for mice is that the genes which are concerned with smell are found on the same part of the genome as the genes that control how the immune system decorates cells so they can recognise each other. And so the idea is that if mice smell alike, they probably have a very similar immune system as well. And the problem with this is that if you have an immune system that's too similar, it shows you're very genetically related. And so if you have your smell system programmed to recognise someone who's very closely related to you, it means it's a bad idea to mate with them. And people have done experiments. If you take a male mouse and a female mouse and they're brother and sister, if you force them put them in a cage environment where they haven't got any choice, then they will mate with each other and have offspring. But if you introduce a second mouse, so you've got the mouse's brother and then another male mouse that's unrelated, then the mouse will preferentially mate with the one it's not related to. If you introduce the second mouse after the mouse has already mated and is already pregnant, it can abort the pregnancy and then mate with the new mouse. So they are very strongly trying to avoid incest at all costs, it would appear.
That's interesting. I think it's probably worth mentioning that sometimes it happens the other way. I mean, the ancient Egyptian royal family actually used to promote incest because they thought it was a good thing.
But were there consequences? Presumably
there were. And Tutankhamun, of course, sort of famously had a club foot as a result.
Fascinating. Now, Dave, this one here, we mentioned this at the beginning. David Goodman says, what would happen if two lightning bolts were to collide or hit each other?
Well, a lightning bolt is essentially a very, very large spark. This is when you have a very, very large charge building up on something. It's so large that it can rip the electrons off air molecules, and then that suddenly means that air goes from being an insulator to a plasma, and a plasma has free electrons moving around. Therefore, it conducts electricity really well. That means the path which this has happened to it becomes very, very conducting, so it kind of attracts all the other little lightning bolts and all the other charge from around it. And so all that charge runs down one single lightning bolt all the way down to the ground. And I think lightning bolts hit each other in the sky all the time, and essentially they would just pick the path of least resistance, and all the current from both of them would go down the path of least resistance to the ground.
And they carry a huge current, 20,000 amps or so, I read, and it's enough to heat the air in the area of the lightning bolt to about 30,000 Kelvin, or 6 times the surface temperature of the sun, which is why you get this huge expansion and a shockwave.
Which is the thunder, of course.
Robin in Norfolk says, "Hi, Naked Scientists. I am an athlete, and I wanted to know where in the world is the best place to run a marathon if the course is flat, bearing in mind the rotation of the Earth and any gravitational pulls from the North or South Pole." The point is, Robin, if you're running the marathon, you're presumably in a race with lots of other people, and so therefore it is, relatively speaking, a level playing field for everybody. The difference, I would argue, though, would be the altitude. Because if you were to go up a mountain and run, if you live up a mountain and you train regularly at altitude, then your body undergoes all kinds of adaptations in order to make you tolerate that high altitude much better. For example, you make more hemoglobin, the red stuff in your blood that carries oxygen around the body. You also have muscles that are much better able to tolerate lower oxygen tension, and they make other chemicals, including one called 2,3-bisphosphoglycerate. I know this because I've been teaching medical students at the university this recently, and this goes inside red blood cells and makes them give up oxygen from their hemoglobin more readily. So if you went in a marathon with some people from Kenya who all live and train at high altitude, which is why they always do very well in marathons all over the world, you would be competing as someone who doesn't live at that altitude. You don't have the same genetic ancestry that makes that beneficial for you, and therefore you would be at a disadvantage compared with someone who does. Diana, now it's time to answer another very important question, which is the business of Question of the Week.
It is time for that, and this week it's been a rather sort of circular week.
Hi, this is Alina Roberts from Corvallis, Oregon. I was wondering if you could tell me if the blind are able to walk in a straight line, or if the sighted with a blindfold can walk in a straight line.
And who's better at walking in a straight line, blind people or blindfolded people?
So my name is Jan Saumann, and I used to work at the Max Planck Institute for Biological Cybernetics in Tübingen in Germany. Yeah, that's a very interesting question. I guess most people intuitively would say that blind people will be better at walking a straight line than sighted people when blindfolded, because of course blind people have been used to not seeing all their life and therefore probably develop some strategies of coping with that handicap. It actually turns out that blind people are not better at that than sighted people. So people have done two kinds of studies. One kind of study is just exactly that test, just have people walk in a straight line while either blindfolded or being blind, and see how well they do. And it turns out that blind people don't do better than sighted people who are blindfolded. And the other test that has been done is have people walk in a curved path by holding on to something that guides them on this curved path, and then have people judge whether they're curving to the left or to the right. And again, it turns out that blind people are not better at that than sighted people who are blindfolded. The problem for blind people is so big that sometimes it happens that when blind people try to cross a wide street, so a multiple-lane street, that they end up at the same side of the street where they started from. So they actually walk half a circle while trying to cross the street. It's actually not that surprising if you think about it that blind people are not better at walking in a straight line than sighted people, because the brain of people trying to walk in a straight path while blindfolded or blind only has, so to say, internal information. So only information that comes from the body itself, from the sense of balance, the vestibular organ, from the muscles and the tendons in the body and so on. And all those cues only give information about the relative changes in walking direction. So with every step, it basically tells the brain whether it's still going in the same direction or veering a little bit.
So why might this be?
Because those signals are kind of noisy signals, they're biological signals, so there's some kind of noise in those signals. There will be small errors in those signals, and those add up over time, and therefore you end up walking in circles, because that's just the accumulation of errors over time. That works the same way for blind people as for sighted people who are blindfolded. So that might be a plausible explanation why people walk in circles when they get lost or when walking blindfolded, and also why blind people are not better at it than blindfolded people.
Unfortunately, brain inputs are often subject to small errors, so walking in circles can be quite a common occurrence. On the forum, Seawolf suggested that some people have a dominant side of their body, leading to imbalances in the steps they take. This is true, but in Jan Suman's research, he tried to control for this by x-raying leg lengths and even building up one shoe without the subject knowing. But next week, try getting down the road without any shoes.
My name is Jane Britton-Long and I'm from Newnham-on-Severn in Gloucestershire. Ever since I did my physics O-level in 1985, I have wanted to know the following. If you have a car with a rear spoiler bar on the boot area, most pimped up or customised cars have this bar. It looks like a shopping trolley handle on the back. And a man of average height, say 6 feet, and weight, say 10 stone, if he took hold of this bar and the car drove away, how fast would the car need to go before the man is airborne? I know that the outcome would not be pleasant, but theoretically I just find this really interesting.
It does look like a shopping trolley handle sometimes.
There'll be people who have pimped their ride all over the place and mortified now they've heard that.
Well, how fast do you think that car needs to go? Answers to Chris at thenakedscientist.com or write on the forum, and that's at thenakedscientists.com/forum.
Diana O'Carroll. So if you have any great questions that you would like Diana-lised, then do send them in to Chris at thenakedscientist.com. You might want to consider sending in your questions about the atmosphere and airborne pollution next week, because we're covering the fact that scientists have been taking to the air, flying back and forth across the UK at night to measure pollution. We'll be talking to the guys and going airborne with them to find out how that works and what they've discovered. And we'll also be talking to engineers who are building a tube which is 20 kilometres long to reach right high up into the atmosphere and take and deploy samples. That's all coming up next week. Send your questions to Chris at thenakedscientist.com. In the meantime, thank you to our wonderful production team, Mira Centerlingham, Tom Simpkins and Ben Vousler. And until next time, goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.